video is on rotational motion and angular velocity. This is an introduction to the topic. So rotational motion is similar to linear motion, which involves objects moving on a straight line. For example, a car driving on a highway. Rotational motion is similar to that, but it involves an object rotating about an axis. So a cooling fan on a ceiling, for example. And these two motions are very similar. It's just that the variables change. For example, here you can see velocity final and velocity initial equals angular velocity final and angular velocity initial, represented by the W. And acceleration becomes angular acceleration. Change in x or displacement becomes change in theta or angular displacement, but change in time remains the same. So we can see in this table how the equations translate from UAM to U angular acceleration motion, or uniform angular acceleration motion. We see how the 5 variables translate to the other 5 variables from linear to angular. And then we can see in these 4 equations how the variables plug in and replace the variables. For example, in the first equation we can see velocity final equals velocity initial plus acceleration times change in time, which is a UAM equation. And then in the uniform angular acceleration motion equations, we see angular velocity final equals angular velocity initial plus angular acceleration times time. So this is an introduction on going from linear motion to angular rotational motion.
To introduce angular velocity, we'll first start with linear velocity, the equation being v equals change in position over change in time. But this change in position is in one direction. Angular velocity, represented by little omega, this little squiggly w right here, is equal to the change in angular position over the change in time. Angular position being represented by theta. Angular position is the place around the center of this circle here. An example would be if a ball started here, rotated counterclockwise, and ended here. But to measure this, you will need units. The most common unit in physics is the radians per second, but the most common unit in the real world will be revolutions per minute, which you can see next to the speedometer in your car. It is important to note that angular velocity is a vector quantity. If the object is rotating counterclockwise, the vector will pop out of the page. If the object is rotating clockwise, the vector will go into the paper. A good way to remember this is the right-hand rule. If the fingers are pointing in the direction of the motion, then the way the thumb is pointed is the direction of the vector quantity. A useful equation to know is W equals V over R representing radius, and this is what you will use to convert between linear velocity and angular velocity and vice versa.
Alright, when first dealing with angular acceleration, there's a few things you need to know. The first is that angular acceleration is represented by the lowercase Greek letter alpha. And basically all angular acceleration is a change in angular velocity over time, which can be represented by this equation up here. The average angular acceleration is equal, again, to the change in angular velocity over time. Now, the units used for angular acceleration are going to be in radians over second squared or revolutions over minute squared, but the basic SI units for angular accelerations are going to be in radians over second squared. Now, the equations most commonly used in this class dealing with angular accelerations are very similar to the UAM equations we used earlier. Like an example is the angular velocity is equal to the initial angular velocity plus angular acceleration times time, which again is very similar to one of the first UM equations we learned. Now I'm going to show you a real-world application of angular acceleration. Alright, so right here I'm at my turntable about to demonstrate some angular acceleration. And remember, angular acceleration is the change of angular velocity over time. Now here I have a medallion over my turntable, and as I turn it on, it plays with a constant angular velocity. But as I turn the pitch down, and as I increase it at a constant rate, you are adding an element of angular acceleration.
Alright, so let's go over what we've learned. Rotational motion is an object rotating on an axis. To find rotational motion, we can use formulas that are similar to UAM equations except with different variables. These variables are things like angular velocity final and angular velocity initial. Some variables remain the same, like time. From rotational motion, we can lead into angular velocity. Angular velocity is a vector quantity. You can find angular velocity by dividing the change in angle measure by time. It's measured in radians per second or revolutions per minute. By finding out angular velocity, we can figure out angular acceleration. Angular acceleration is equal to angular velocity over time, which is equal to radians per second squared. An example of a formula where you have to find angular acceleration is angular velocity final equals angular velocity initial plus acceleration times change in time. I hope you've learned a lot from this video.